This is going to be a quick review of material for the second exam in Chemie 350 this spring. So what we've covered since the last exam essentially is distillation. So if I'm going to draw a diagram of a distillation column, and you've seen this a bunch of times, we've got the column itself, vapor leaving the top of the column, goes through a condenser, into the reflux drum, we pull out a distillate, there's the reflux going back to the column with flow rate L. At the bottom of the column, we have a reboiler, which is an equilibrium stage producing a liquid bottoms and a vapor boil up that goes back into the bottom of the column. The feed enters the column on this side, defining two sections, a rectifying section and a stripping section. The main control parameter we have over this column is the reflux ratio, which is defined as the liquid flow rate going back from the reflux drum over the distillate flow rate. Also, from an engineering point of view, we have the fundamental trade-off that we have to consider. And this is the same as the trade-off that we saw for absorbers and strippers, and that is simply the trade-off between number of stages and amount of material separation agent. In this case, instead of entering a stripping gas or an absorbent, we have the reflux ratio controlling the amount of material separation agent. And in this case, as the reflux ratio approaches infinity, that is total reflux in the column, the number of stages necessary to perform a given separation is going to approach a minimum. Similarly, as the number of stages approaches infinity, in other words, the pinch point for the column, we have the reflux ratio approaching a minimum. Reflux ratio is going to reflect the column's operating costs, whereas number of stages reflects the column's fixed costs. The main technique that we learned for designing a distillation column was the Mccabe-Thiele procedure. And this worked by drawing on XY space, where X is the liquid phase composition for our light key, and Y is the vapor phase composition. And this is not a dilute system, so we're drawing the full equilibrium range from 0 to 1, so 0% of our species of interest, our light key, to 100% of our light key. And we always draw in a 45-degree line to act as guidance, and because it provides the intersection for the compositions, distillate bottom and feed compositions. And then we have the equilibrium curve, which describes the equilibrium between our light key and our heavy key. And so again, this is our 45-degree line. So the first thing that we can do is we can identify 3 points. We can identify the bottoms composition, we can identify the distillate composition, and we can identify the feed composition. This gives us the 3 points at which our two operating lines for the rectifying section and the stripping section, and our Q line for the feed intersect the 45-degree line. The next step is to draw the Q line. We know that the Q line is going to intersect the 45-degree line at this point, at ZF. Now we merely need to find the slope of the Q line in order to draw that Q line. So if you recall, Q is simply equal to the amount of liquid in the feed over the total feed flow rate, the liquid flow rate in the feed over the feed flow rate, so it's the percent of the feed that's liquid. And if we have a saturated liquid, of course, Q is going to be equal to 1. If we have a saturated vapor, Q is equal to 0. Now, of course, Q itself is not the slope of the Q line. When we do the material balance, we find that the slope of the Q line will be Q over Q minus 1. So when we have a saturated liquid, Q equals 1, we have a Q line with an infinite slope, in other words, a vertical line. When we have a saturated vapor, Q equals 0, we have a line with 0 slope, in other words, the Q line is horizontal. For some composition in between saturated liquid and saturated vapor, we're going to have a Q line with an angle that looks like that. The next step is often to find the minimum reflux ratio. The minimum reflux ratio occurs when the rectifying section operating line has a pinch point with the Q line. So we need to draw in the corresponding rectifying section operating line. That'll look to the pinch point like that. All right, the slope of this line is simply Rmin over Rmin plus 1. All right, so once we find the slope, we can measure the slope, and then we can find Rmin. And then typically, we are given R as some multiple of Rmin. And so then, once we have the actual R, we can find the actual slope of the rectifying section operating line. This is the same equation. It is simply R over R plus 1. This allows us to draw in the actual rectifying section operating line, which is going to have some slope less than the slope of the Rmin rectifying section operating line. We then draw in the stripping section operating line from the intersection of the Q line and the rectifying section operating line to XB rather, on the 45-degree line. And now we can count out the number of stages. We transition from one operating line to the other when we cross the Q line. And so here we have 1, 2, 3, 4, 5, about 5.5 stages. The feed stage is the stage where we cross the Q line. This is stage 4. That allows us to find the optimal feed stage location. The bottom stage is the reboiler. So for this column, we have 1, 2, 3, 4.5 stages on the column, and the 5th stage is the reboiler. At this point, we've already talked about one of the extreme conditions. That's where we reach the minimum reflux ratio at the pinch point between the rectifying section operating line, the Q line, and the equilibrium curve. This corresponds to an infinite number of stages as we work through the pinch point there. And this is the relationship between the slope of the rectifying section operating line and the minimum reflux ratio. The other extreme condition is achieved when we have a minimum number of stages corresponding to an infinite reflux ratio. At an infinite reflux ratio, so recall R equals L over D, which means that as D approaches 0, R goes to infinity. And so this is the situation that we call total reflux. And if D is equal to 0, then we also have F equal to 0 and B equal to 0. In other words, there's nothing entering or being taken out of the column. We just have the fluid in the column being continuously recycled. And in this case, we can do our Mccabe-Thiele diagram, and we showed that for total reflux, the 45-degree line is coincidence with both the stripping section operating line and the rectifying section operating line. And there's no Q line because there's no feed, so we can merely stair-step as follows. Between XD and XB. So here we have the reboiler, and 3 stages on the column in minimum reflux conditions. I'm sorry, 3 stages on the column in infinite reflux conditions, total reflux. So this construction allows us to begin to look at column efficiency. What this gives is the number of theoretical stages at total reflux. Of course, we can operate an actual column at total reflux, and we can measure XD and XB for that actual column. Then we can perform this Mccabe-Thiele construction and figure out how many theoretical stages that column operating actual reflux corresponds to. We know the number of trays on the actual column, so we can simply find the overall efficiency of the column by taking the number of theoretical stages from the Mccabe-Thiele construction at total reflux and dividing it by the actual number of stages on the column that we are operating at total reflux. Another approach to efficiency is to look at Murphy vapor efficiency together with the Mccabe-Thiele construction. So you will recall that Murphy vapor efficiency is simply the amount of the change in concentration in the vapor phase over an actual stage over the change of concentration in the vapor phase that would occur if we approached equilibrium completely in that stage. So Yn here is the actual concentration that would be achieved, whereas Yn star is the equilibrium concentration that would be achieved. So we can draw both of these on a Mccabe-Thiele diagram. And it's simply like this. So at any point in this diagram, we can draw the following construction. This point here is essentially Yn plus 1. This point here is going to be Yn star. Right? On the operating line, we have the relationship between xn and Yn plus 1. Then on the equilibrium curve, we have the relationship between xn and Yn. So the fact that we don't fully approach equilibrium means that we only go some distance up this line during the process. And this will be our actual liquid phase composition, Yn. So if we label these points A, B, and C, the Murphy vapor efficiency is simply going to be equal to the amount that we actually approach. So this is the length of the line segment AB over the amount that we would approach if we achieved complete equilibrium. So this is simply going to be the length of the line segment AC. And we can repeat this construction all the way up and down the column such that the ratio of the line segments is always equal to the Murphy vapor efficiency. And once we do that at a few points, we can draw in an effective equilibrium curve that passes through these points Yn. And then we simply perform our standard Mccabe-Thiele construction. Right? Same as we always do with a Q line, a rectifying section operating line, and a stripping section operating line. But now, instead of stepping all the way to the actual equilibrium curve, we step to this effective equilibrium curve that we have created by looking at the line segment difference for the Murphy vapor efficiency at several points along the length of the column. We also talked about how to select a condenser type. The process is simply as follows. First of all, we find the condenser pressure necessary to get a condensed distillate. At this point, we can decide whether we need a total or partial condenser based on whether this pressure is sufficiently low. If the pressure is low enough, we use a total condenser. If we need a higher pressure than our system can tolerate, then we're going to need to use a partial condenser at a lower pressure. Once we know the pressure at the condenser, we can use the column pressure drop to figure out the necessary temperature at the reboiler in order to produce a boil-up vapor. And finally, we make sure that this boiling point in the reboiler is acceptable if it is low enough to avoid decomposition of any of the species that we are trying to purify. If the temperature is too high, then we're going to need to go back up to the condenser and operate that condenser at a lower pressure in order to get a lower temperature in the reboiler. And when we design a column with a total condenser, we simply do our same Mccabe-Thiele. And now, just as the bottom stage is our partial reboiler, an equilibrium stage, our top stage is going to be our partial condenser, again an equilibrium stage. And then the stages on the column are the ones that are not stage 1 or stage N. We also learned how to handle multiple feeds on a distillation column. The key here is that each feed creates a new vapor and liquid flow rate. So we can think of this now as, instead of a 2-section column, a 3-section column. Right? Whereas previously the single feed divided the column into a rectifying section and a stripping section, now we have a rectifying section, a stripping section, and what we would call the interfeed section. And of course, what defines a section is a change in liquid and vapor flow rates, which corresponds to a change in the slope of the operating line for that section. The slope of the operating line is simply going to be V over L for a given section. And just as a single feed changed V and L between the rectifying section and the stripping section for a single feed column, now with 2 feeds we have a third V over L, a third operating line slope. So just as before, we use a Q line. So for each feed, we continue to have Q is equal to L for that feed over the total feed flow rate, right? So the fraction of each feed, that's a liquid. So this gives us a Q line for each feed. And we draw the Q lines just as we have before, from the slope that we get, and intersecting the 45-degree line at, in this case, we're going to have F2 over here and F1 over here. And so we can draw on those Q lines, whatever their slope may be. And then we draw on the rectifying section operating line at XD. Based on the slope given by the reflux ratio. And then for the interfeed section, we need to find what the vapor flow rate over the liquid flow rate is in order to get the slope of that operating section. And that's going to be accomplished by performing a material balance between those 2 feeds, which you can do if you know what F and L is for each feed. All right, and that will give us an operating line with a different slope. And then we do the same thing for the stripping section that we did for the standard Mccabe-Thiele. We simply draw a line from XB on the 45-degree line to the intersection between the interfeed operating line and the Q line for the second feed. And then we proceed as we always have. Now we have 2 feed stages. Right. Again, the feed stages occur on the stage that crosses the Q line. So this is the stage corresponding to feed 1, and this is the stage corresponding to feed 2. And finally, we discussed how to design packed distillation columns. We described essentially 2 methods, one based on the height equivalent to a theoretical plate, our good old HETP, And we simply said that HETP was going to be equal to the height of the gas phase mass transfer unit to a simple solution for the integral that is NOG. And this is going to be ln of lambda over lambda minus 1, where lambda is equal to the slope of the equilibrium curve times v over L. All right, so this is the slope of the equilibrium curve, m, and it is going to be different at each stage, right? Where each equilibrium stage touches the equilibrium curve, we have a different slope for the equilibrium curve at that point. If we assume constant molar overflow, V over L is simply the slope of the operating line, so it is going to be different in each section. And we also showed that we could express HOG as a gas phase portion plus lambda times a liquid phase portion, where the gas phase part of HOG is equal to the vapor flow rate over the mass transfer coefficient, the microscopic mass transfer coefficient, KYA, times the cross-sectional area of the column. And HL, the liquid portion, is equal to L over the microscopic mass transfer coefficient in the liquid phase times the cross-sectional area of the column. So what we wind up with is, again, we draw our Mccabe-Thiele diagram, and we say that for every stage, we can find a lambda. Lambda allows us to get this value. And then if we're given an HG and an HL, we can use lambda to find HOG. And then lambda and HOG will give us the height equivalent to a theoretical plate for each stage. And we merely add those heights together to get the total height of the packed column. Our second approach to solving packed columns involved coming up with an explicit integration of the NOG integral. And the way that we did that was we said that we had separate solutions in the rectifying section and the operating section. So in the rectifying section, the total length of that section, R for rectifying section, is going to be equal to the vapor flow rate over, again, microscopic vapor phase mass transfer coefficient times the cross-sectional area of the column. And then we integrate between the feed and the top of the column the gas phase concentrations, gas phase mole fractions of dy over the interfacial or the equilibrium gas phase mole fraction minus the variable, the y variable, the gas phase mole fraction, right? We're integrating in terms of that variable. All right, and then in the stripping section, we now use the vapor phase flow rate in the stripping section, which we've called V bar. And again, we have the gas phase microscopic mass transfer coefficient and the cross-sectional area of the column. And now we are integrating between the bottom of the column and the feed, the same integral. And as we've stated previously, the problem with doing this integral is that we don't necessarily have a functional relationship between yi or y star and y. So the way that we establish that is we again use a Mccabe-Thiele construction. At this time, we're not going to bother stepping for individual stages. We will simply draw in our Q line, draw in our rectifying section operating line, and draw in our stripping section operating line. And now what we say is that there is going to be a relationship between each point xy and an interfacial point xi, yi. And that relationship is given by the slope of this line, which we get from mass transfer analysis as negative kxa, the liquid phase microscopic mass transfer coefficient, over kya, gas phase microscopic mass transfer coefficient. So given the slope of this line, we can find a yi for every value of y. So we can simply numerically integrate from the bottom of the column to the top of the column by drawing these lines with a constant slope and finding the value of yi for each y. So do a simple Riemann integral, and you have solved the height of each section. You add the height of each section together to get the total height of the column. That's it for the review.